All right, welcome to the online lesson for Friday, September 27th. This is going to be primarily a review lesson. I wanted to put everything that we've learned, or the really critical things that we've learned together here so that you can review and make sure that you have a grasp on the basic concepts that we need to have mastered in this unit on propositional logic. We're going to review a couple 3 or 4 main things. We're going to look at the 5 logical connectors, make sure we understand how they're symbolized. And then at the end of the lesson, I'm going to provide you with the truth tables for each of the 5 kinds of complex propositions. We will look at how to identify the main operators in a formula. We did this in class last time. I have a few more exercises to look at there. And I want to look at the criteria for determining whether a formula is well formed or not. And we'll have some practice exercises related to that. So, to review, we've seen that negations are going to be symbolized using a tilde, the squiggly dash. Conjunctions are symbolized using a dot. Disjunctions are symbolized using a wedge. Implications are symbolized using the sideways horseshoe, and equivalencies, or what are called biconditional statements, are symbolized using a triple bar. And please remember that Van Cleve does not introduce the equivalency symbol, or the triple bar, because it's technically superfluous. You can generate a biconditional by creating a conjunction of 2 conditional claims, or 2 implications. If you refer to the slide, you'll see that I've assigned meaning to each of the uppercase capital letters, which is what Van Cleve refers to as a constant. Those stand for discrete propositions, and in this case, they're defined off to the right-hand side of the slide. So F means freedom consists in being able to do whatever one pleases. R means freedom consists in being responsive to reasons. And C means freedom is consistent with one being legally restricted from doing whatever one pleases. Now, referring to that key, we can go through each of the 5 examples that I've provided here and see what each means. So starting with the negation, not F would be read in English as meaning it is not the case that freedom consists in being able to do whatever one pleases. Moving on to the conjunction, R.C, or R and C, would be read as meaning it is both the case that freedom consists in being responsive to reasons and freedom is consistent with one being legally restricted from doing whatever one pleases. Moving on to the disjunction, that would be read as stating either it is the case that freedom consists in being able to do whatever one pleases, or freedom consists in being responsive to reasons. The implication, or the conditional claim, would be read as stating if freedom is consistent with one being legally restricted from doing whatever one pleases, then it is not the case that freedom consists in being able to do whatever one pleases. And the biconditional, or the equivalency, would be read as stating freedom is consistent with one being legally restricted from doing whatever one pleases if and only if it is not the case that freedom consists in being able to do whatever one pleases and freedom consists in being responsive to reasons. So take a second. If you need to review that, push pause and review that. Make sure you understand why I read each formula the way that I did. And if you have any questions, make sure you jot those down in your notes. Moving on, in class we looked at how to recognize main operators. To do so, we have to identify the logical operator that contains everything else in a formula within its scope. Or in other words, find the logical connector, or the operator, that ranges over everything else in the formula. And so I've given you 3 examples here. Take a minute or a second to see if you can identify the main operator in A. So the main operator here is the implication sign, or the horseshoe, because it contains as its antecedent the constant a, and then as its consequent that biconditional formula. Take a minute or a second to see if you can identify the main operator in B. Oh, I'm sorry. There's an error on the slide. The red circle should be around the dot. Everything shifted when I changed the font. But anyways, the main operator here is the dot. So the left-hand conjunct is the disjunction of not A and both B and C. And then the right-hand conjunct is the implication if E, then F. Moving on to C, the main operator here might be a bit difficult to discern. We have to recognize that it's the negation sign. The negation covers everything else in the formula. So in other words, what the tilde does in this formula is it negates everything else. And that's because of how the brackets work. So we're working initially from the curly bracket. The curly bracket contains within it a disjunction. The left-hand disjunct is A if and only if not B. The right-hand disjunct is if C, then it is both the case that not A and B. But all of that is negated by the tilde. So the tilde is the main operator. Now, what we call a well-formed formula, or logicians call them WFFs, because it's WFF, a well-formed formula is a formula that is syntactically correct. And what this means, there's three criteria that we want to look for. Tildes are all placed immediately in front of the statements they modify. And keep in mind that the tilde is the only logical operator which is not a connector. It is only a modifier. All other operators, the wedge, the dot, the horseshoe, or the triple bar, have to be placed between two statements that they modify. So they are always connectors. And the range of each operator has to be properly indicated using parentheses, square brackets, and curly brackets. So take a look at this list, and you can push pause here. Figure out which of the following are well-formed formulas. Once you're done, push play and I'll walk through the answers. Okay, number one is a well-formed formula. The negations are properly placed. The range of operators is properly indicated using parentheses and square brackets. And in this case, this formula is a conditional claim. And we would read that as it would say, if it is not the case that A, then either B or C, if and only if not D. Number two is not a well-formed formula, because if you notice, we have both a wedge and a dot, and there are no parentheses to indicate over which atomic propositions those connectors range, or what their scope is. And there's no way for us to determine what the scope is. If you are given a poorly formed or an ill-formed formula and you have no original paragraph or verbal argument to compare it to, there's often no way to turn it into a well-formed formula, because we don't know whether this should be properly read at the highest level as a conjunction or as a disjunction. Number three is also not a well-formed formula. Here again, neither the conjunction symbolized by the dot nor the disjunction symbolized by the wedge have their range specified using brackets. Number four needs a connector. If you notice, the formula within the curly brackets is, that subformula is well formed, but it's followed immediately by not O, and there's nothing connecting the sub-formula within the curly bracket with not O, the negation of O. Negations cannot function as connectors. They are only modifiers. Number 5 is a well-formed formula. It is a conditional claim or an implication. The antecedent of the conditional claim, is itself a disjunction of not A on the left-hand side, and then the further conditional claim, if C, then both not A and B. So that's the whole antecedent clause, and then the consequent clause is not D. All of the range of each operator is specified properly. Negations are not out of place, and so on and so forth. 6 is not well formed because if you notice, both the first wedge following not F, and the conditional symbol, the horseshoe, that precedes the last disjunction that says not H or H, they do not have their range properly specified. And finally, 7 is not a well-formed formula either, because neither the wedge nor the triple bar has its range properly specified. Okay, as I've said, propositional logic can only analyze arguments that are composed of compound statements that can be interpreted as truth functions. And a compound statement is a truth functional claim when its truth value is a function of the truth values of its component atomic propositions. Now, what this is going to mean is that if we tabulate all of the possible arrangements of the truth values of component atomic propositions, and if we understand how the logical connectors work, we can develop tables that indicate under which circumstances a truth functional claim would be true and under which circumstances it would be false. A simple example of a disjunctive truth functional claim is what I have here. Either Chris enjoys watching Good Mythical Morning or he enjoys watching Food Wishes. As we've seen in class, this is composed of 2 atomic propositions, and there are going to be 3 possible worlds in which the entire disjunctive proposition is true. And that's what I've indicated here. So if you, so we have the proposition up top in quotation marks. And we've had this on the board in class before, but I'm putting it here just to review and for your reference. When we have 2 atomic propositions, there are going to be 4 possible arrangements of truth values because truth is considered binary. A proposition is either true or it's false. There's no such thing as a proposition that is both true and false, and there's no other third option. So I populate my truth table initially by taking the total number of possible arrangements and dividing by 2. And under G, I've listed TTFF, meaning G can either be true in 2 possible worlds or false in 2 possible worlds. And in the first possible world, its other disjunct, W, is also true, but in the second possible world, W is false. In the third possible world, W is true, and in the fourth possible world, W is false. Those are the only 4 possible arrangements. Now, given what we know about the disjunction, as we've said, it is inclusive, which means that truth functionally, it is a disjunction is true whenever at least one of its atomic propositions is true. So that means that there's only one world in which it's false, and that's the world, the logically possible world in which G is false and W is false. If you understand the logical connector, you can create these truth tables because you look at the component parts, the atomic propositions, and their truth value. So starting on the first line, the first possible world, if G is true and W is true, then the disjunction as a whole is true. If G is true and W is false, the disjunction as a whole is true. If G is false but W is true, it's true. But again, if both are false, then the claim as a whole is false. The negation is exactly the same once we understand that the negation works by negating the truth value of whatever its atomic proposition is. We can generate a truth table. This one's very simple. So the example I have here is, it is not the case that Chris enjoys watching any of the Real Housewives shows. So the atomic proposition here is Chris enjoys watching any of the Real Housewives shows. We'll call that proposition R. But the claim as a whole is a negation. So I negate that atomic proposition. And what that means is a world in which it is true that Chris enjoys watching any of the Real Housewives shows, it is false that it is not the case that Chris enjoys watching any of the Real Housewives shows. In a world in which it's false that Chris enjoys watching any of the Real Housewives shows, then it's true that it is not the case that Chris enjoys watching any of the Real Housewives shows. We got to get used to the fact that we're going to speak in double negations in a case like this. Take a minute, make sure that you understand what's going on here, and if you don't, jot that down in your notes so we can talk about it in class. Moving on to the conjunction to review this truth table. We've already seen this in class, but as a reminder, a conjunction is true only in a logically possible world where both atomic propositions are true. So unlike the disjunctive claim, which is true in 3 possible worlds, the conjunctive claim is true only in 1 possible world. It's only true in a world in which both G and W, in this case, are true. In any other possible world, at least one of the conjuncts is false, and so the overarching complex conjunctive statement is itself truth functionally false. We talked about the conditional claim at length in our last class period. The conditional claim is very complicated, as we saw. The example I have here is, if Chris is a fan of Aaron Sorkin's work, then he enjoys watching Newsroom. So that's what we call the material conditional. And again, there are 4 possible arrangements of truth values since I only have 2 atomic propositions. We lay out the truth table as we have in the other cases where we had 2 atomic propositions. But the conditional claim is true in every possible world except one where the antecedent is true and the consequent is false. The reason that we say a conditional claim is true in a logically possible world where the antecedent is false is because in such a world we lack any logical reason to suppose it's false. I'm going to go through this I'm going to pause and dig a little deeper into this to remind you of what's going on. So as I've been using the phrase antecedent and consequent, and I introduced this in class last time, the antecedent in a conditional claim is whichever atomic proposition is on the left side of the horseshoe, and the consequent is the atomic proposition that is on the right side of the horseshoe. As with all compound claims in propositional logic, we are going to assume that conditionals assert a truth functional relationship. And the reason I want to emphasize this is, although they are sometimes called hypothetical claims, we really need to interpret conditionals in the indicative mood. That is, they assert something. We can't interpret them in this, what grammarians call the subjunctive mood. When we refer to the subjunctive mood, we're referring to a form of speech in which we assert that something may or may not be the case. And that's a natural way of reading an if-then claim. It seems hypothetical. But for our purposes here, we are not assuming that conditional claims say, well, maybe, like if I have the proposition if P then Q, we are not interpreting it to mean something like, well, maybe P, maybe if P then Q, or maybe Q. We're interpreting it as asserting a material conditional relationship between the propositions. That's what we were talking about in class last time. Whenever what we need to know is that whenever the antecedent is true in a conditional claim, the consequent must also be true. And whenever the consequent is false, the antecedent must also be false. That's the kind of relationship between atomic propositions that we interpret if-then claims to be asserting. Okay, so returning to the example, if I am a fan of Aaron Sorkin's work, then I enjoy watching Newsroom. The question is, why must we say that the claim is true in a logically possible world where I'm not a fan of Aaron Sorkin's work, but I do enjoy Newsroom? And at issue here is that nothing about the truth values of the atomic propositions suggests that the claim is truth functionally false once we understand how we're interpreting the material conditional. In this case, it could be that I hate all of Aaron Sorkin's other television shows, but happen to like Newsroom. And a similar thing goes for a possible world where I'm not a fan of Aaron Sorkin's work at all. I don't like any of his TV shows, and I'm not a fan of Newsroom. So if I don't like any of his work, and I'm not a fan of his show Newsroom, it's the claim. If Chris is a fan of Aaron Sorkin's work, then he enjoys watching Newsroom, is still interpreted to be truth functionally true because I lack any evidence that it's impossible. Okay, so this is what I want you to make sure you have in your notes and you try to wrap your head around. The only possible world in which a conditional claim is truth functionally false is a world in which the antecedent is true and the consequent is false. In every other possible world, it's truth functionally true. Okay. I don't know if this is going to be helpful to anybody else, but when I was a student in my undergraduate logic class, I realized that when I lay out the truth table, as I have it depicted here in the bottom right corner of the screen, the world in which the conditional claim is false, as you see, is a world in which the antecedent is true and the consequent is false. And it looked to me like like if I tried to sound that out phonetically, it looks like tough. And so I think I try to remember that I use the mnemonic device tough luck. In every other possible arrangement of truth values, the horseshoe is listed as truth functionally true, but not when it's TF. When it's TF, then it's tough. So if that helps you, use it. If it doesn't, I don't know what to tell you. Try to figure it out. Okay. One of the things that comes out of this discussion is, I already mentioned this, but in a world in which the antecedent is false, any world in which the antecedent is false in a conditional claim is a world in which that conditional claim is true. And that seems weird. So if I say, for example, if the moon is made of Swiss cheese, then chickens can hatch elaborate escape plans. Turns out, from a truth functional perspective, that's a true statement. And if you want to make true statements, just make if-then claims where the antecedent is clearly false. So you could generate true claims very easily, truth functionally true claims very easily by constructing an if-then claim in which the antecedent is an absurdly false claim or an absurdly false proposition. All right, back to our other connectors. The biconditional, this is the one that Van Cleve does not introduce. The biconditional is stated using the English phrase if and only if. So here's an example. I could say, Chris enjoys watching the show House of Cards if and only if he enjoys watching political dramas. There are, again, because we have two atomic propositions, 4 possible arrangements of the truth values of the atomic propositions. And a biconditional claim is going to be true in every world where both atomic propositions have the same truth value. So if you look at the truth table, in the first possible world, the claim Chris enjoys watching House of Cards is true, and the claim Chris enjoys watching political dramas is true. That means that the biconditional claim is truth functionally true. In the last possible world, it is false that Chris enjoys watching House of Cards, and it is false that Chris enjoys watching political dramas, so the biconditional claim is itself true. In any world where the two atomic propositions connected by the triple bar have divergent or different truth values, the biconditional claim is false. Okay. I need you to make sure that you know that you can generate the truth tables for each of these 5 types of complex propositions. If you need to, you can memorize the truth tables, and that's a place to start if that's where you're at. But ideally, you want to get to a point where it's not simply that you've memorized the truth tables, but that you understand the truth functional relationships that underlie the truth tables. So in your as homework and as you're working through Van Cleve's text, make sure you're grasping that. And if you aren't understanding it, or if you don't feel like you have a good grasp on that, try to formulate a question that we can address in class on Monday. I really need all of us to get on board with the truth functional relationships, the kinds of relationships that each symbol asserts, so that we have an understanding of how these logical operators are meant to work. What we're going to be doing next week is developing more complex truth tables for more complex compound propositions that contain multiple connectors, multiple logical operators. All right, if you have any questions, you can email me, or as I said, bring questions that would help you clarify and better understand things to class on Monday. Thanks.